in this tutorial, I'm going to explain the basic idea about effect size. So effect size quantify the strength or relationship between variables or the magnitude or the differences between groups. So if like we are compare different groups, then we can use Cohen D. So this is the formula to calculate the Cohen D. So the mean differences divided the standard deviation. And if it's two variables, both of them are on a continuous scale or both of them are numerical, then we can use Pearson correlation. So this is the Pearson correlation formula to calculate the Pearson correlation R. Based on Jacob Cohen, that the small, medium, and large effect size, they are slightly different when comparing the Cohen D and correlation R. So 0.2 is considered as small for Cohen D, but for correlation coefficient, 0.1 is considered small. I'm going to explain what it means, why they are different. So I have two commas here. So one is that Cohen D can be from 0 to infinity. So even though these three numbers all then are smaller than 1, but actually Cohen D can be greater than 1. In contrast, the Pearson R typically is in the range of -1 to 1. And here, when we're talking about small, medium, and large, we're talking about absolute value. But I mean, Pearson correlation can be negative. Another one is that actually this is my personal note. In my opinion, not sure 100% correct, but my understanding is that Cohen D can be negative as well. Why? The reason is that, for instance, if the M2 is smaller than N1, then the numerator is negative, and the denominator always positive. That means that it can be negative. That's just my understanding. It could be wrong, so there's no guarantee, but I feel like Cohen D can be negative. That's my understanding. If you have any questions, feel free to comment down below. And if I make a mistake here, you can also feel free to point it out. And another one is that, okay, we see that the numbers are different here in terms of small, medium, and large for Cohen D and correlation coefficient R. So actually you can convert one to another. There's a formula to convert that. For instance, here you can convert R to D, vice versa, you can convert D to R. Okay, so now knowing the basic idea about Cohen D and correlation R, I'm going to go to using some R code to demonstrate these two measures of effect size. So this is the R code. Basically, I wrote the PDF. It just show using the R model. So this is the R code. So basically, we're going to simulate X and Y. Both of them are numerical data. So basically, both X and Y are on a continuous scale. And so by doing that, so we set the C, we set the mean of X, mean of Y, standard deviation of X, standard deviation of Y. And then we also predetermine the value for correlation coefficient 0.5. Notice that this is the theoretical value, and eventually we simulate the data, it has some randomness. So, but the value, when we calculate the correlation coefficient, it should be pretty close 0.5, even though they are not exactly the same. It will not be exactly the same as 0.5. Okay, so let's run it. So you simulate the data here, and we print out the first 6 row data, X and Y. As you can see that both X and Y are numerical, yes. So we can plot the data and also add a trend line here. And we can also calculate the correlation coefficient to see what the value is, yes. We expect it should be close to 0.5. So here is 0.52, which is not exactly the same as the value we predetermined 0.5, but they are pretty close. Okay, so remember earlier we talked about that actually the Cohen D and correlation coefficient actually you can convert one to another. And we know that Pearson correlation coefficient R is for both x and y are numerical. And in order to use Cohen D, basically you need to make the x variable as categorical variable. One way to do that, basically, we can just like dichotomize the x. Yes. So based on if the mean of x is, if the number is greater, for instance, if this number, let's run it. Basically, this code is dichotomize the x based on the mean of x. So if a number, for instance, this is a continuous scale, yes. If this is smaller than the mean, we call it as 0, and if greater than the mean, we call it. So this is still smaller than the mean, so it's 0. But this is greater than the mean of x, so we call it as 1. And here again, this is smaller than the mean, we call it as 0. So basically, the idea is that we can create a column of data, 0 and 1 binary based on the mean, each value of x to compare its mean. So we can do that. So now we have x is binary and y is continuous, so we can use the Cohen D to calculate the effect size. So here is the R code, and basically, because this is the formula to calculate Cohen D. Yes. So since that x is binary, we can basically calculate mean for group 0 and group 1, and then calculate standard deviation, and then calculate Cohen D. So this is basically the R code. I basically just using this formula to calculate the Cohen D, and we run it. So the Cohen D is 1.25. As you can see that the x basically is kind of the binary version of x here. But as you can see that the effect size is Cohen D 1.25. But actually, it's consistent in terms of correlation 0.52, even though they look different. That goes to the core idea is that Cohen D and correlation R, they look different. That's the basic idea. I don't know whether you get that or not, but if you still have question, let me know. So another way to calculate the Cohen D is that since that we already know the correlation coefficient R, we can convert it to the Cohen D. And we'll expect that the Cohen D should be pretty close. Yes, so we can write this. Basically, this R code just write out this formula statement. So we get the correlation coefficient this is not correlation coefficient, even it has correlation coefficient. This is actually the Cohen D, but it's R code, it uses the COR, the variable named here, but this is actually Cohen D. As you can see that this Cohen D 1.226 actually is pretty close to the Cohen D you would directly calculate. So we use the conversion method, we got the similar Cohen D value that we directly use this formula. So they're pretty close. So you can see that there's some connection between Cohen D and correlation coefficient R. Okay, I think that's it. So in this tutorial, I basically explained the basic idea about Cohen D and correlation R, and I use R code. I generate the data, and then also generate the data set, and then show you that in the connection between Cohen D and correlation coefficient R. If you have any questions, feel free to comment down below, and I will do my best to answer the questions you might have. Okay, thank you for watching. So basic idea is that you can using the R code to write out to calculate the correlation coefficient, and then basically just write out this whole formula. But of course, you can just like do some manual calculation. You can also do some manual calculation by yourself. Yes. So let me write here. So basically, what we are doing here is we just like based on this is the correlation coefficient we calculate earlier, yes, we already know that is 0.52, yes. So this is the correlation coefficient. We directly use the R code to calculate the correlation coefficient. So 0.52 we can write out here. So it's like 2 times 0.52. And then the denominator is, okay, I'm using R markdown here. FICSM. Okay, oh no, sorry. SQRT. 1 minus the 0.52 square, yes. So basic idea, then we should expect that this will get the 1.2. So basic idea is that the basic idea here is that, okay, you do not you can just directly, based on the correlation coefficient, you can just also convert it to the Cohen D, which is 1.2. So the R code here just write out this calculation process. But you can also do some manual calculation you want. You got a 1.23, 1.2, so 1.2. So I think that's it.